All right, so in the previous video, we saw how to take a rational expression and represent it as a partial fraction decomposition, which made it easier to integrate. We only looked at one case, though, and that was the case where you end up with this rational expression here, r of x over q of x, and that q of x in the denominator in our first case was able to be factored into a product of distinct linear factors. Sometimes that's not the case. Sometimes your factorization of q of x might include a factor that looks like this. So what we're seeing here is a linear factor, ax plus b, but it's repeated, meaning you could represent it as being raised to some power where that power is 2 or greater, okay? When that happens, the way that we do a partial fraction decomposition is a little bit different. So let's suppose that we have in our q of x a factor of this form, ax plus b to the power of r, where r is some positive integer that's greater than or equal to 2, okay? Then what that's going to tell us is that when we do the partial fraction decomposition of this rational function, part of the sum will look like this. Notice that I have a sum of rational expressions where I also have constants in the numerators like we did previously. But now my denominators look like this, this linear factor here, the ax plus b, but being raised to increasing powers. So for example, ax plus b to the first power is what I'm seeing here. And then ax plus b to the second power is it's a different denominator, but that's showing up here. Next would be ax plus b to the third power. That's like the next thing once we get to this dot, dot, dot right here. And that continues all the way on until I get to whatever power r I raised this thing to originally, okay? So it's a little bit different. That's that one, factor where we have a linear expression raised to a power produces all of these terms here. So let's see how that would play out in an actual example. This is going to be a definite integral. It's the only definite integral that I'm going to do in this section, but you may see more in the homework. We want to evaluate the definite integral from 2 to 3 of this rational expression right here. X times 3 minus 5x all over 3x minus 1 times x minus 1 squared, okay? Now, this one is kind of nice because there's two things that we're not going to have to worry about in this example that we did have to worry about in the previous example. The first thing is that I don't need to do long division here, and here's how I know that. If I were to distribute this out, my x here, I would get a quadratic polynomial in the numerator. That means the degree is 2. If you were to multiply out your denominator, you would see that you have a third degree polynomial. And hopefully you know how to determine that without actually having to multiply that out. That's something you should have spent time in algebra doing. How can I look at the factored form of a polynomial and immediately know what its degree is? But I can see that this would be a 3. So my denominator already has a bigger degree than my numerator. That means we don't have to do any long division, which is nice. The second thing that's kind of been done for us is my denominator is already factored, which is also super convenient because that's another step we usually have to worry about. So what I'm going to do is I'm going to write this out. I'm going to multiply my denominator out so that I can write it in the form negative 5x squared plus 3x. You can see that distributing the x and maybe rearranging some terms would give me this. And then I have the denominator, which I'm not going to change in any way. It's going to look like 3x minus 1 times x minus 1 squared. Okay, so what I'm seeing here is one linear factor that is not being repeated. So that's going to show up as the denominator of just one of these terms over here. But then I have another factor, x minus 1, that is a repeated factor. It's showing up twice in this factorization down here. So according to how we deal with this, we're going to include a term where it looks like a constant over just x minus 1 to begin with. But then we're going to include another factor, c, over x minus 1 squared. Now let's say hypothetically that 2 there was actually a 4. Then my partial fraction decomposition would have all of these terms, but then I'd also have to add a d over x minus 1 to the third power, and then plus an e to the x minus 1 to the fourth power. You can see how we're counting up with those exponents until we get to whatever that number is. okay? So now I'm going to do the same thing that I did in the previous example. I'm going to clear all of these denominators out by multiplying both sides of this identity by this denominator here, 3x minus 1 times x minus 1 quantity squared. Okay, so obviously on my left-hand side, that's going to leave me with just that numerator. But what about the right-hand side? What's going to happen? I have a over 3x minus 1. So when I multiply by this 3x minus 1 will cancel with that one. And I'll be left with a times x minus 1 squared there. Okay? And then my b over x minus 1, what happens here? Well, the 3x minus 1 that I'm multiplying by has nothing to cancel with, so that's going to still be there, 3x minus 1. And then the x minus 1 squared, one of those will cancel with that x minus 1 there, but I'm going to have another one left over because that's x minus 1 squared. We only lose one of those factors here. And then what's going to happen with this last term? We'll have c in the numerator. Now I have x minus 1 squared and an x minus 1 squared in the denominator. Those will cancel completely this time, and I'm just left with 3x minus 1. Okay? So now we get to the step where we're trying to figure out what a, b, and c are. So let's see if we can work that out. As before, we're going to plug numbers in for x because we know that both sides of this equation have to be true for any value that I plug in for x. It's an identity. We're going to pick values of x that conveniently cancel or eliminate some of the unknowns. For example, if I plug a 1 in for x, first of all, on the left-hand side, I would get negative 5 plus 3, which is negative 2. On the right-hand side, two of these terms here have an x minus 1 in them as one of its factors. And I know that if I plug a 1 into either of these factors here, all that is going to go to 0. So all I'm left with is c times 3 times 1. Remember, we're plugging a 1 in for x, minus 1. That's 3 minus 1, which is 2 times c. So I would write that as 2c. You notice how this big, ugly equation or identity gets trimmed down to something very, very easy to solve. That tells me that c is equal to negative 1 when I solve that. So we've got 1 down, okay? Let's try and find something else to plug in that's convenient. Well, what we have seen is that when we plug in a number for x, that makes one of these factors in parentheses become a 0. That's been really helpful. So let's do that for the 3x minus 1 term. If I plug x equals 1/3 into that, that's going to produce zeros here and here, which is going to allow me to solve for that a term. So let's figure out what that would look like. I'm plugging a 1/3 in here. 1/3 squared is 1/9. And so that's going to give me negative 5/9 for this, right? Negative 5/9. Okay. Now, if I plug a 1/3 in here for this 3 times x here, 3 times 1/3 is just 1. So I get plus 1. That's pretty easy to do mentally because 1 is the same thing as 9/9 minus 5/9 would be 4/9. Okay. Now, plugging a 1/3 in on this side, what's going to happen? Well, like we said, these two terms are going to go to 0. So I'm going to be left with 1/3 minus 1, which is negative 2/3. But then I'm going to square that, which is 4/9 times a. Okay, so I have 4/9 equals 4/9 a, which implies that a is equal to just 1. Okay, so we've gotten 2 out of the 3 things that we were looking for. That leaves me with b, but that presents a little bit of an issue because the only 2 different types of factors that we've seen here are the x minus 1s and the 3x minus 1s, each of which showed up in a couple of places. If I plug in those convenient values that turns any of those factors into 0, I always lose my b because b is being multiplied to both of those factors. So what do we do here? Well, so far I've only been plugging in numbers for x that have been sending one of my factors to 0, but there's no reason you have to do that. You can plug other things in for x also. For example, what if I were to plug in x equals 0? It doesn't have to be 0. I can plug something else in, but 0 is usually a convenient number to work with. So I'm going to go ahead and just try that. The left-hand side, all of my terms have x's. That whole left-hand side is going to go down to 0. What happens to my right-hand side? Well, starting with this first term, I have 0 minus 1, which is negative 1, squared, which is positive 1, times a, which is just a. But I don't need to write an a because I already know what a is. A is equal to 1. So that entire first term becomes 1. Here, remember, we don't know what b is, but I am plugging numbers in for my x's here. If I plug 0 in for both of these, I'm going to get negative 1 times negative 1, which is positive 1, times b is just b. Okay? And then here, I plug a 0 in for x. I get negative 1 times c, so minus c. But c, we know, is negative 1. So if I subtract a negative 1, that's the same thing as adding a 1. Now, it's easy to solve for b. b has to equal negative 2 in order for this side to add up to 0. And now we have all three of the numbers that we needed. So this is where I get to rewrite my integrand in a simpler form. Okay, so now what is the integral that we're actually evaluating? The integral from 2 to 3 of a over 3x minus 1. What was a? It was 1. So that becomes 1 over 3x minus 1. Plus b, which we found was negative 2. So I'm actually going to write that this way, minus 2 over x minus 1 plus c. What was c? It was negative 1. So let's write that as minus 1 over x minus 1 quantity squared dx. Now I'm just going to integrate each one of these terms one by one. So that's going to give me this first term, 1/3 natural log of the absolute value of 3x minus 1. That is one of those types of rational expressions where it's 1 over a linear factor. And again, we know how to do those. You would use a u substitution, but at this point we can do it without having to write all of that stuff. Hopefully, you can do that. Then I have minus 2, and that would leave me with 1 over x minus 1, whose antiderivative is the natural log of the absolute value of x minus 1. And then here, this term, you would make a u substitution. You could set u equal to x minus 1, which would reduce this thing down to 1 over x to the x to the second power. I'm sorry, u to the second power, or u to the negative 2 power. There's a minus in front of that as well. My du is going to look like a negative dx. All of that stuff put together is going to give me this, plus 1 over x minus 1 as my antiderivative. And we're evaluating this from 2 to 3. Okay? So at this point, because it's a definite integral, we just need to start plugging some of these numbers in. Let's do that. If you plug a 3 in, you're going to get 1/3 times the natural log of 3 times 3, which is 9 minus 1, that's 8. Okay? Minus 2 times the natural log of 3 minus 1, which is 2. So this is 2 natural log of 2. Minus, I was getting mixed up where I was, plus 1 over 3 minus 1, which is 1/2 there. So plugging a 3 into all of these terms produces this. Then I subtract, plug a 2 in next. 1/3 natural log. 2 times 3 minus 1 would be 5. So I have 1/3 natural log of 5. Minus 2 times the natural log of 2 minus 1, which is 1. Plus 1 over 2 minus 1, which is just 1. Okay, so a couple of things I can do here. First of all, the natural log of 1 is 0, so that term goes to 0. I can do something kind of clever to combine some terms here. So 8 is the same thing as 2 cubed. And we have a logarithm property that says if you take a logarithm of something to a power, that power can be brought out and multiplied to the front. But I already have a 1/3 there, so multiplying it by 3 is just going to produce a 1. Now I have the natural log of 2. That's what's left. Minus 2 natural log of 2. These I'm going to treat like terms, which I can combine. Then I have plus 1/2, but I'm going to distribute this minus sign in here, and there's going to be this 1 here that I'm subtracting. So 1/2 minus 1 would be negative 1/2. And then I also have this negative 1/3 natural log of 5 there. Let's do that last thing that I said I was going to do. Combining these gives me the minus natural log of 2. Let's move the natural log so they're all together. Minus 1/3 natural log of 5 minus 1/2. And this is as simple as I think I'm going to make this. It is possible to simplify it a little bit further, but that's good enough for me. Okay, let's leave it at that. So there we go. There's another one down. Let's keep working through the other cases. So case 3. This is where we start looking at quadratic factors. So Q of x contains irreducible quadratic factors, none of which are repeated. This is what we're going to call case 3. An irreducible quadratic factor means you have a quadratic polynomial, something like this, ax squared plus bx plus c, that you cannot factor down to a product of 2 linear factors. Now, technically, every quadratic can be factored into a product of 2 linear factors, but a lot of the time, in order to do that, some of your coefficients have to be complex numbers. And we're not dealing with that sort of thing here. So what we really mean is that they are irreducible over the real numbers. That means that it's impossible to factor an irreducible polynomial down to a product of linear factors where all of the coefficients are just real numbers. That's a little bit more specifically what we mean by that. Okay? If that happens, let's suppose that you have an irreducible factor, ax squared plus bx plus c, as one of your factors of Q, then that's going to produce in your partial fraction decomposition a factor or a term of this form. So notice there is that same quadratic factor showing up in my denominator. I cannot factor it down any more than that. And my numerator now, instead of just being a constant, is a linear polynomial, ax plus b. Okay? That's where this is different from the previous cases. So let's take a look at an example. I have 3x squared minus x minus 8 over x cubed plus 4x. Remember, the first thing we want to do is compare degrees. Now, the degree of my denominator is 3, which is greater than the degree of my numerator, which is 2. So that means I get to skip any long division. It's nice when that happens. My denominator is not factored yet, so I'm going to want to factor it. So we can write it this way, 3x squared minus x minus 8, same numerator. I can factor an x out of my denominator, which gives me x squared plus 4. Now, this is an irreducible quadratic factor because it's a sum of squares. We know that a difference of squares can be factored down to, like if it's a squared minus b squared, you can factor it to a plus b times a minus b. But you cannot factor a sum of squares without using complex numbers. So that this is as good as we can make this. Now what I'm going to do is write it as a sum of terms that create a partial fraction decomposition. And notice we have a mix of different types of factors here. I have one linear factor, which is just the x, and one irreducible quadratic factor. So each of those kind of does its own thing. This x, being a linear factor, is going to produce something like this, a constant over x, so a over x. This irreducible quadratic factor, according to what we have here, has to produce a linear numerator, bx plus c, over the original quadratic factor. Okay, so my partial fraction decomposition is going to look something like this. We proceed the way that we've been doing these problems. Multiply both sides by this denominator, which will just leave me with a 3x squared minus x minus 8 on the left. On the right, these x's will cancel and leave me with a times x squared plus 4. On this side here, the quadratics will cancel, and I'm going to just have an x there, so plus bx plus c times x. Okay. Now I'm going to go ahead and proceed here the way that I've been doing this, but I want to just make a quick mention of something, and that's something I alluded to earlier. There are other ways of solving for these unknown constants, the a, the b, and the c. One technique that's usually taught when people do this is to actually multiply everything out on this side. So if you notice, if I multiply the a out, I'm going to have a quadratic here. If I multiply this x in, I'm going to have a quadratic here. And so I have a quadratic when I combine all of my like terms. And you want to do that. You want to combine all of your like terms. So there's only one x squared term, only one x term, and only one constant showing up. Because this is an identity, this polynomial has to be exactly equal to this polynomial no matter what I plug in for x. But that can only happen if the quadratic on this side has all of the same coefficients as the quadratic on this side. So the idea in that approach, if you want to use that fact, is, again, you multiply all of this out, combine everything so you have just an x squared term, an x term, and a constant, but all of those are going to be in terms of these unknowns, a, b, and c. You can set those coefficients on the right-hand side equal to the coefficients on the left-hand side, and that produces a system of linear equations, which you can then solve using whatever method you like. That works perfectly fine. In my opinion, it takes a lot more time to do that for most problems. You may come across a problem where that's actually the best approach. My personal opinion is the way that we have been approaching these is just generally more efficient. So with that, let's keep plugging away. What is a convenient number that I could plug in here to eliminate some of this stuff? I think x equals 0 is a good starting point. And that's because this x here, when I plug a 0 into it, will zero out this entire thing. It gets rid of the b and the c simultaneously, which is really nice. If I plug a 0 in over here, I'm left with my constant term, -8. Over here, 0 squared plus 4 is just 4. So I get 4a. This would mean that a is equal to -2. So that's pretty nice. We got a solution for that. Okay, here's where we can do something kind of interesting. So these two polynomials, like I've been saying, they form an identity. This has to equal this no matter what you plug in for x, and that actually includes complex numbers. We can plug complex numbers in for the x's, and these still have to be equal. The reason I'm saying that is because if you're looking at this other factor right here, and you do what we've been doing, you're saying, what can I plug in for x to make this thing become 0? There are no real numbers that would do that, because any real number I plug in for x here is going to produce a non-negative term here, and then I add a 4 to that, and that could only ever be something positive, never 0. But if you plug in the complex number 2i in for x, 2i squared is equal to 4i squared. But remember, I squared, by definition, is -1. So when I square 2i, I get -4 here. Plus 4 would be 0. Okay? So I can do that. That's actually fine to do. And the way that we deal with what's left is kind of interesting. So let's think about this for a second. I have to plug 2i in for everything. I know this will become 0, but the other stuff may not. So once again, we said that 2i, when I plug it in here, 2i squared was -4. Then I'm going to multiply that by 3 to get -12. Okay? Minus x, we're plugging in 2i, so I get minus 2i minus 8. Okay? So that's the left-hand side, and we'll combine some stuff in a second. On my right-hand side, I'm going to have this go to 0, and over here, I'm going to have b times 2i, which I'm going to write as 2bi, I like to keep the I at the end, plus c times 2i. Okay, now I'm going to simplify both sides. So here, -12 minus 8 would be -20. And then that minus 2i doesn't have any other I terms to combine with, so it's still minus 2i. On my right-hand side, if I distribute this 2i in, the 2 times 2 here becomes 4. The I times I here becomes I squared, which is the same as -1. So 4 times -1. This whole thing becomes -4. b. Don't forget that the b is there. C times 2i. C is just some real number, so that becomes 2ci. Okay? Now what I have is a complex number on the left and a complex number on the right. If you remember from your work with complex numbers in previous classes, complex numbers have two parts to them. They have a real part and they have an imaginary part. The real part of this complex number is -20. The imaginary part is -2. Not -2i, it's just the real number in front of the I. We call that the imaginary part. Two complex numbers are equal to each other only if their real parts are equal and their imaginary parts are equal. So what does that mean? That implies that this -20 has to be equal to that -4b right there. Real part equals real part. This -2 right here has to be equal to that 2c right there. Imaginary part equals imaginary part. That allows me to solve for b and c at the same time. Solving this gives me b equals 5. Solving this gives me c equals -1. And now I have all the things that I need. I have a, b, and c. Those can be plugged in up here to give me a better, something else that I can represent this thing as. So now let's think about what this looks like. I have the integral of a over x, but a we found out was -2. So I'm going to write that as -2 over x plus bx plus c. So that's 5x plus c would actually look like -1 over x squared plus 4 dx. Now, this guy right here, you might look at that and think, well, that still doesn't look like something that I can readily integrate, you know, because as I see it, I still have this like linear thing over this quadratic thing, but there's a way to deal with this without trying to do any more partial fraction decomposition, because we've already done the partial fraction decomposition. We can't do anything more to that. First, if I integrate this term, this one's easy. That becomes -2 times the natural log of the absolute value of x. But now what I'm going to do is I'm going to take this rational expression and split it up into two separate integrals. So first of all, I can write this as 5x over x squared plus 4 minus 1 over x squared plus 4. But make each one of those its own integral. And I'll bring the minus from the -1 out also. 1 over x squared plus 4 dx. Okay? Now, this can be solved with a u substitution. I can set u equal to x squared plus 4. So let's do that. U equals x squared plus 4, which means du is going to equal 2x dx. I have a 5x dx, not a 2x dx, but if I multiply both sides of this by 5/2, then that's going to become 5x dx. So that's a substitution I can make for that 5x dx right there. Okay, so now what we end up with is -2 natural log, this comes down here, -2 natural log of the absolute value of x, plus, let's do the u substitution. I'm going to get du over u here. And then this guy, this is easy to integrate because it's of this form. It's coming back over here. It's of this form. 1 over x squared plus, in our case, 4. But 4 is 2 squared. So this is what I have here, but the a is equal to 4. So a is equal to 2. So if I plug a 2 in for the a's here, I'm going to get plus the inverse tangent. I have a 1/2 on the outside, I almost forgot to write, of x over 2. Now all that's left is to deal with this final integral right here. I know that this would be equal to the natural log of u. So natural log of the absolute value of u, but I don't really need to write the u because I need to convert it back into x's again. X squared plus 4 is really what that's equal to. Okay, plus 1/2 inverse tangent of x over 2. And now that I don't have any integrals left, I need to make sure I'm including my plus c in there. All right, another one down. Just a little bit more to cover. We'll do that in part 3.